Okay, so welcome to the second part of the seminar. So this part is not related to the first part, it's independent of it. And it's about regularization. So we already talked a lot about optimization. So here on the left, I'll show you again this picture of sort of the general problem or the general setting of machine learning, where we specify a hypothesis space. We have a truth that is up here, typically outside of our hypothesis space. And we have an optimization procedure here. And there's sort of an optimal approximation, the best that we can achieve within a hypothesis class to approximate, to be the closest to the truth here. And that is this problem of generalization. And we talked about this before, and today I want to kind of concentrate on minimizing this generalization error. So getting us closer to this optimum here. We discussed this here last week. So we said that if we have the capacity, so think again of the capacity as a number of parameters that you have, sort of the size of your hypothesis space. And we can drive down the training error by making, having more and more parameters until we kind of, fit the data. However, if you fit the data exactly, the testing error may go up because we just overfit. So this is a sort of classical overfitting. So here we do underfit, and here we would do an overfitting. We also talked about that in deep networks, we have this sort of double descent. But I want to kind of keep at this sort of overfitting, underfitting problem and discuss that. So how can we somehow reduce the capacity of our model, which in this picture here, we can interpret as how do we explore this hypothesis space in order to get close to this point here. Okay, so that's a general setting. And in this picture here, we fix the number of data points. So now we can fix the capacity and see how does the training and testing data behave when the size of the data increases. And so for the training, we see that the error actually goes up. And because we are outside of, we don't recover the truth, we recover the closest approximation. So that's what we would call the bias. But then if we will have like a small training error, so we might just say we're much better here. However, then we have a large variance here for the testing error. So each time we apply our learned network to unseen data, we might get something completely different. So we have a high variance model. So that's something we want to control as well. There's sort of a trade-off between bias, having a low bias, and having a low variance. So we're going to discuss all those different ways of controlling them. And again, this is just focusing on minimizing this distance here. That's this generalization gap that we try to address through these regularization procedures. So it's an overview of what type of regularization strategies we're going to discuss. So there are different strategies. They address different kind of problems, and some are more and some are less useful for deep networks. So we start with sort of the classical regularization. That's where we just impose some norm penalties. So that's something that most people would be familiar with. Then a technique called data augmentation, where we just try to increase the number of data so that we decrease the generalization gap. We can add noise to help with regularization. We're going to explore that. There's something that's widely used in deep learning, which is very cheap strategies called early stopping. And then we're going to spend some time on ensemble methods. So it's something called bagging or bootstrap aggregating, and something called dropout that we're going to discuss. They're kind of popular methods for regularizing networks, deep neural networks. But let's start first with regularization via norm penalties. So by putting a norm penalty, we sort of reduce the capacity somehow. We don't allow all norms, all weights, but the weights should be somehow restricted in norm. And sort of the second idea that's related to that, that by doing that, we impose some sort of prior knowledge onto the that we may have onto our weights. So we're going to have capital I stands for regularization. We're going to modify the objective function or the loss function L that depends on the data, x, y, and our weight by taking the one that we like to have, like the mean square error or cross entropy, whatever you have. And we put a norm constraint in here. So the omega, capital omega of W is just the norm constraint, and we can choose any norm we like. Then this problem here, if you interpret this as a Lagrange parameter, you can see that this is equivalent to the following optimization problem, where we just minimize the loss function, our original loss function, subject to the constraint that the norm is bounded by epsilon. Okay. And sort of important remark, typically only the weights are, you remember there's always an affine transformation there. So there are weights and there's a bias, and typically it's only the weights that are sort of penalized. The reason being that a bias is quite easy to fit, doesn't need as many data because it just affects one variable, right? It's just plus B. Whereas the weight matrix affects two variables, right? The input and the output. So you need many more data to explore all the different possibilities. So you would need more data to fit the weights than to fit the biases. So that's why typically you only penalize the weights. Okay. All right, so let's start with the kind of most familiar one, the L2 regularization, which is also known as Tikhonov regularization or Ridge regression. So that's when this norm constraint is just the L2 norm of the weights. Okay. And so here is just a schematic how it works. So our original function, let's say, is this L here. So these are contour lines in L. Just assume it's in R2. And this is our constraint to lie, the norm constraint, Euclidean norm less than 1. And so you can't get the absolute, you can't find the minimum here because it's not admissible with the constraint to be inside or on the circle. So you're going to be on the circle here, so where you tangentially touch it. And what you can see here is this distance is much smaller than this distance because you have here the directions in which the weights reduce the L's significantly, which is this one here, where we have a much steeper, like if we do cross section, it's a much higher curvature in there. So that's where we can learn quickly, and that's why the W is going to be found the minimum. Whereas in this one where we have less curvature, that's where the regularization acts more. Then you will be familiar, I suppose, with linear regression. So that's when we impose a linear model. So our hypothesis space is just out of linear combinations of the inputs, affine linear combinations of the inputs, and we do a mean square error as our cost function. Then this is what we would get for our weights. And so you see we have this inverse of this matrix. Lambda is this regularization parameter. You see if lambda is 0, if you don't do any regularization, it will require that this matrix is invertible. So if we are underdetermined, so if we have many more parameters than we have data, then this matrix is typically not invertible, and regularization is actually needed to get a solution at all, right? You can relate them. So the lambda is like, they're kind of inversely proportional, right? Sort of the smaller, the smaller you force your constraint, right? Your ball around 0 for the W's, that means the stronger your penalty constraint is here. Okay, so in here the epsilon doesn't occur, right? So but if you think of this as, do you know Lagrange parameters, like sort of constraint optimization problems? You want to minimize this function here subject to some kind of constraint. Now you want to an inequality constraint. Now you want to write this as an equality constraint. And if you have an equality constraint, you want it to write it as something that I can just like have some kind of function called Lagrange function that I can just do my normal kind of calculate the gradient. And the price you pay is that you augment the dimensions. So you're not just minimizing with respect to W, but also with respect to lambda. And so the derivative with respect to lambda would give you your constraint back. So you could write, if you want to, maybe that makes more clear. And then this is like the constraint minus epsilon, let's say. Right. So we were here in this picture. And just by looking at the picture, again, we said in this direction, the constraint is not doing too much, the regularization is not doing too much, whereas here in this sort of flatter direction, we have much more of a correction, okay? And you can see that in here as well, where we expect regularization to work and be important. If you interpret this XTX, well, it's a covariance matrix. So when you do an SVD, let's say you find out those directions in which the covariance, is small, so in which the data are sort of compressed, and it's those directions that these kind of uninformative directions of low variance, where adding some lambda onto those SVDs, will matter. Okay. There's some drawbacks here. So you can get stuck by just imposing this this constraint. You can get stuck in local minima just by imposing a constraint. So these were local minima, would be local minima that that would correspond to small norm, but you want to, there might be a big gap to the actual global minimum. So that's one problem. Another problem is that you could have a positive feedback. So let's say you start with some large weight, then because then the penalty will imply a large gradient. So you will have a large change again in the weights, and that will that can become an instability. So these are problems that may occur. And what people tend to do in practice is they first minimize just the actual objective function, the L of W, in one step, let's say using stochastic gradient descent, and then you just project onto the closest W that falls inside that admissible region. That's one way people get around this. So they really then look at it in this way here and enforce this by hand. There's another, well-known regression or norm regression, which is L1 regression. So that's where, we take the sum of the absolute values of the weights and restrict them to be less than some value here. So this is now the admissible region. And then, so what you see here, if I now want to minimize my L, is that this promotes sparsity. So here we're going to have W1 is going to be 0 and W2 is something that's non-zero. Okay. And that allows to do something that people call, well, it's feature selection. So you might want to do that even before training a neural net, because you have, you just kill certain entries of your input, and then you have a feature selection that is easier, has of lower dimension, that then is easy to train and to feed into a neural net. And just to mention the name lasso, so this famous that you may have heard when you look into optimization procedures that people use. So it stands for least absolute shrinkage and selection operator. And you can sort of map this minimization problem into something that is, obviously convex if your L is convex, but just having some constraints. And again, by augmenting the space, and you also would need to, optimize for those UIs here. That's just to kind of mention that people do that. Yes, so Wij is now, I just make it into one long vector Wi. Then I mentioned at the beginning that there's some prior knowledge that we could use, and that these constraints or these regularizations, they sort of encode some prior knowledge that we may have about the function. So we could have a constraint here, a norm constraint, but on a norm of this reproducing kernel Hilbert space of some function G. And so here's just one example that's sort of widely used, are these Gaussian kernels. Okay. And if you calculate the norm of this in this reproducing kernel Hilbert space, then the norm looks like this. So, if it's Gaussian, a Fourier transform of a Gaussian is a Gaussian. So the F are the Fourier modes here, Fourier components. And so you can see that if I want to restrict the norm, you're going to restrict the, the energy that's in the higher Fourier modes. And this exponential factor makes it like for really high Fourier modes, you have even more kind of, more constrained. So this constraint, if you were to impose it, would promote smoothness of the function, okay? And so you might have some prior knowledge that the function you expect is very smooth. So then this is a nice way of sort of exploring this hypothesis space and making sure you constrain in the way that is consistent with the function that you're trying to approximate. So if you have some prior knowledge on the function, for example, that it is, it has that is smooth and it doesn't have high Fourier modes, excited, then that is a constraint that allows you to, move into that direction. Yeah. So where your optimization would be close to that optimum if that, yeah. So this is a very simple idea here, the data augmentation. So the idea is just what we're after is we want to minimize the loss function here, where we take all the x and y's just from the distribution that's given to us by the data. So over all the data that are possible. And if we interpret this average here sort of as this sample average, then if we take more samples, we should get a better estimate of that expectation value. So more data is typically good for decreasing the generalization gap and reducing the generalization error. So one example where this has been used is in CNNs. So where you can create kind of your artificial new data by slight rotations or by small translations. So a cat that's translated is still a cat that's rotated is still a cat. So if you know something about those symmetries, that you expect, you can use them. Be careful, I guess, if these symmetries are not actually there. You don't want to impose symmetries that may not be there. And also the type of the imposed symmetries that you use or the may depend on the problem. For example, if you want to distinguish handwritten numbers, you don't want rotations by 180 degrees because a 6 then becomes a 9. Similarly, if you want to look at individual letters, you don't want to do a flipping. You don't want to allow flipping, right? I mean, so the type of symmetry really is that you're going to use, and how you create this data, how you do this data augmentation is model dependent or problem dependent, I should say. Okay. Now comes a sort of more interesting way of doing regularization, and that is to add noise. And you can add noise to the data. So this is similar to data augmentation. You got your data, you add some noise, you get some new data, and you train your model on them. And you can show that relatively easily that if your loss function is the mean square error, and if you have linear models, then this is equivalent to some L2 regularization. Okay, so something that we already discussed. But you can also add noise to the weights, and that gives a different constraint, and that I'd like to discuss. This way of adding noise to the weights, that is actually often used in the recurrent networks that Joel just described, apparently, and sort of it reflects a Bayesian perspective on regularization. In a Bayesian perspective, you consider the data not as something that's randomly drawn. The data are there, and there's only one set of data. There's one set of world, one world, and the randomness is in the parameters that you estimate. So you don't think that there's a true parameter. You think there's a distribution of those parameters. Okay, and so if we just put some noise on those weights, we kind of work in this framework where we think the data are kind of real and fixed, and then we have some distribution over those weights, and we assume there's some kind of distribution that we can then use that assumed prior distribution to modify those weights. And so what do we do? And can we relate what it would do to our optimization? So Joel just said that there is a distribution that works for PyTorch that uses Bayesian computations, and so does assume some probability distribution of the parameters and calculates on the space of probability distributions. Thanks. So how does it work? So let's say we have here our weights. Now we bang on some noise with some, variance epsilon or epsilon squared. And that is the new weight that we're going to use. And let's just assume this psi is normally distributed. So the variance is epsilon squared, but we assume it's small. Now, this is our model here of the perturbed W epsilon. So we can do a Taylor expansion with epsilon small. So this is our model when we were not, weren't perturbing, plus epsilon and this kind of, the next Taylor term. Okay. So let's look at what the mean square error is. So we take the mean square error of our model here minus the data, square it, and now we have we average over the data. Okay, so we just say so here we're going back to kind of treating the data as a random variable, and we average over the independent noise that we use to perturb the weights. And now you can do the square and so forth. If you do that, then what you see, using that the mean of this psi here is 0, that this is the old function, right? The old loss function plus epsilon squared times this function here, where this is like a Frobenius norm on the gradients here, right? On the gradient matrix. So what does that mean? This is now a norm constraint, right? This is a norm constraint that we add up. Epsilon squared is the regularization parameter, okay, that we assume to be small. So what do we promote now? We can ask. We said, we promote sparsity, or we promote that then there's some kind of smallness of the weight. So what do we promote here? Well, these are the kind of the derivatives of the model with respect to the weights. So we want that to be small. So that means we promote that the solution finds weights such that the model is robust to small perturbations of that weight, right? So it's sort of a robustness kind of, it imposes some robustness, okay? So I quite like that. Just the sum of all the matrix entries squared, right? So we want kind of, we're looking for like flat minima in the parameter space. Okay, that's kind of the regions that we're looking for. Okay, and yeah, you see here, if we were to use a linear model, then adding noise wouldn't do anything, right? So if you use a linear model, the gradient is just a constant. There's no, right? We take the gradient with respect to W, so there's nothing to do for us. Okay. Yeah. Sorry. You add. You take the how you would do that, because you need to estimate. You could do it at every step, I suppose. I've never used it, I have to say, so disclaimer. But you could do it at every step of a gradient descent or stochastic gradient descent. I mentioned. There's a second question, or at least there's a. Okay, what's next? Early stopping. So this is a super cheap and because of that also very widely used techniques that people do. So if we look at epochs, so epochs is once we pass all our data through through our algorithm, and then we do it again to kind of converge with the weights. Typically, what you see is that you drive down the training error, and here you see that the validation error, you always reserve some of your data to do validation, to sort of estimate the generalization error. That one goes up again. So because of the overfitting that you will be doing. And so one idea is, why don't we just stop here? Okay, so you just monitor the validation error. There's nothing, you don't need to store much. It's just you do that calculation anyway, and you say, okay, I'm going up, I stop. You just find that sweet spot and you stop. Okay, so very, very cheap. But this is in effect, again, an L2 regularization. Okay, so this is L2 regularization that we discussed. And this is now the stopping rule. So you're going to learn, like, in regions of parameter space where you have high curvature, you're going to learn very quickly. You're going to go down with a fixed learning rate. You're going to go down there quickly, right? And in the ones where you kind of flatter, you're going to learn slower. So you're going to stop. You start. Let's say we start at 0. You're going to stop somewhere here, and that then I can just say, well, okay, there's some kind of equivalent circle around here that I can interpret, as an L2 regularization. So And here we already discussed this. We have, in L2, and for the L2 regularization, we already said we're gonna, the regularization works where the gradient isn't constraining, the optimization a lot, right? Where we have these flat curvature regions. So that's a one-to-one correspondence. Yes, Harini. Can I try to rephrase because there was a question that the type of regularization depends on the model you're using. I would say it does. Well, it's a model and it's also what so it's a hypothesis space in which you work and what you know about, about the data. The question was, is it evident what you'll be using? But it's also problem, like if you want to control this here, you do stopping down, right? If you want to control this overfitting, underfitting, that's a good way of dealing with it, right? It depends also on what you think is the major obstruction to diminishing that generalization gap. Okay, so if you think it's an overfitting, underfitting, you can use that. If you think the problem of having like a large generalization error is something else, like a high variance or something in your model, you may use something else. Oh, so the question is there a relationship between what we learned in the last hour, where we had this problem of the exploding or vanishing gradient? Well, that addresses more the optimization, right? Whereas here we have some optimization and we want to see where do we end up in terms of what what's the best estimate within our hypothesis space that's kind of closest to the truth. Okay, so it's a different question you ask. Thank you. Okay, so that's early stopping. Now, ensemble methods. So in an ensemble method, the idea is the following. We want to generate an ensemble, and I'm not going to specify what I mean by an ensemble. So it could be anything. It could be changing your data, changing the network architecture, changing something randomly that affects the test error, but not the training error. Okay, so I want to still have a good training error, but I want to reduce the test error. So that is the idea of creating these ensembles. And the idea is if you average over this ensemble, then you are better than any individual member of the ensemble in making a prediction, in either classifying or in regressing. Okay, so the idea is like this wisdom of the crowd. Where you have you got a jar full of beans and you ask people independently. So it's important to do it independently, how many beans are in there. And apparently, if you ask a lot of people, you get a pretty good estimate of how many beans are in there. Okay. And so how does this work, and what are kind of what's needed to get this situation where we can reduce or where we can improve on prediction by taking an ensemble average. So let's say we have some kind of ensemble of models that we somehow generated. So we have m different models that we somehow randomly generated. And the mean is some g bar, and then there's some kind of noise term here. And we have some kind of knowledge about the statistics. We know the covariance and so forth of this noise. And then our predictor in the end is the average over all those models. Okay, we add them all up, divide by the number of models we have. That's our predictor. So that should be our g bar plus the noise. Okay, an average of the noise. Now we can ask, okay, what's the mean square, or what's the variance there? What's the mean square error? And if you do that, you get two terms. You get one term here that depends on the variance of each model, and then you have a covariance term here. Okay, so let's say there's no covariance. Every model, each epsilon I is kind of the same, right? So this epsilon j is, it's like an epsilon squared, and so then you subtract that -1 on m from 1 on m, and you basically are just left with the what each individual model does, right? So there's no advantage of doing an average. However, if they're all uncorrelated, that's the other extreme. So if this one is 0 here, okay, so each model gives you completely independent, uncorrelated, no correlation here, then you see, you reduce the sort of variance of each model, which is this, expectation value of epsilon squared by 1 on n. Okay, so if you have a large ensemble, you can reduce that variance. Okay, so this is now, if you have a high variance model, you can reduce it by averaging. So now there's a question, how do you generate the ensemble, this ensemble of models? And I'm going to present to you two different ways of doing it. So one is called bagging, which stands for bootstrap aggregating. Another one is called dropout. So you could think, you could randomize algorithms, you could randomize the architecture, the loss function, the training sets, and so forth. And in bagging, you sort of do something with the training sets. So let's say you have a training set here, X and Y. That's the original training set. And so I've got all these different rows. And now I create M samples of training sets where I randomly pick one of the rows, one of the n rows, there are n rows here. So I take randomly one of the n rows and put it into the first row of my first sample. And then I put it back into my basket. So I have, random draws with replacement, and I draw again, and I draw again, and so forth, and fill up here. So you're going to have repetitions, right? You can kind of easily find out what's the percentage of repetitions, right? I mean, one draws 1 on n. If you want, to draw a particular row is 1 on n. To not draw is 1 minus 1 on n. And now you have to do that for all the n rows. So 1 on n, 1 minus 1 on n, you do that n times. So if your n is really large, this goes like 1 on e. So it's roughly 36% or something like this. Yeah, that you actually have, that you're missing, 36% of the data that you're missing. Okay. And so now you have this sort of, but they're all independently drawn. And now you create from each of them, you create a model. So this would be model G1. This would be the model G2, let's say. This would be the model G3. And this would be the model GM. Okay, so now you have these independent models. They're all, if I now let each of them run on a test, on new test data, they would give us different answers. Okay. Now, if we now do the testing, we want to create this G hat, which is just the sum of them, and then average. Okay, and that is how you do this bagging. Okay, and so this is good for high variance, low bias models. Right, we want a low bias because we want that G bar, our average, to be a good estimate. Okay, if our G bar, which is the best we can do by averaging, right? If we take infinitely many of those samples, we would get a G bar. If that G bar is really far away from, where I want to be, that's not very good. So then I actually would like probably high variance. But if I have low variance, if I have a low bias, I can reduce the variance. Okay, so this deals with this trade-off of bias and variance of the model outputs. It's parallelizable, so each of those models are trained independently. Okay, so that's fine. But you pay the price that you have to store, these networks. And if you take more and more and more, this might be too expensive. Sort of a comment on the independence that we needed. So we said we want those models to be independent or partially independent. Otherwise, we wouldn't get a gain by averaging over the ensemble. You can create, or you do create some kind of independence by, well, first by the sampling, but obviously there is dependence because you sample from the same pot there and have repetitions. But you can do random initialization in your SGD and random selection of the mini batches and so forth to kind of increase that independence. Okay. So that's one way of ensemble methods. There's another one that's called Dropout, and that actually tinkers sort of with the architecture or with the actual network. And so the idea is the following. So let's say this is our fully connected network where we have input X, and let's say we do some classification, so we just have one output Y, and we go through two kind of hidden layers here. Okay. So now we're going to create subnetworks, where with a probability P, we say that one of those units is on or off. Okay, and if it's off, we delete that unit and all its, all its connections. Okay, so this is one example of where we apply, a dropout. So where we select one of those networks. So there's going to be, if there's like n nodes in here, there's going to be 2 to the n subnetworks. Okay, one of those subnetworks has no inputs. That's bad, right? But if you think of really, really wide layers or lots of different layers, the probability of picking that one is very low. Okay, and another way you could, help again or mitigate against choosing these networks here is just put a different probability on the inputs. Okay, so I read in the literature, typically like P for unit here is 0.5. So with probability 1/2, you make it active. Probability 1/2, you drop it. And for the inputs, it's probability 0.2. Okay, to drop it. So it's lower. And now, how does this work? So you don't want to draw, you don't want to now do a sample over 2 to the n networks. That would be far too expensive. So what these people here, Jeffrey Hinton, did is the following. They say, okay, we have some kind of mask vector that tells us, who is on, who is off. Okay, and ideally what we would like to do is, average over all those mask vectors. Okay, and what they do is the following. You do it in the gradient descent. So we have here a gradient descent step, stochastic gradient descent. So there's only a certain batch that we use here from our data to calculate the loss function. And then for each example of the data, and also at each time step n, we choose a different mask. Okay, so we go through all the optimization, we take all these different masks, and in the end, we're going to end up with some weights. Okay, we minimize and find convergence, and then we stop. Okay, so it's just one training. It's not one application of a gradient descent. But once you train it, you have to rescale the weights. So think of this. Think this is in training. You have a node here that's present with probability P or not, or 1 minus P. It's not present, and it has these weights W. Okay, that's how we calculate it. But in the end, for the testing, we have the full network where each node is present. Okay, so if I want the expected expected outcome to be sorry, if I want the outcome of this one here to be equal to the expected outcome when I have all these these random networks, then I just have to scale. Kind of I put the P from here into the weights, right? I get just the P times the weight. So that's one way of this rescaling that's done after the training. So you train your network, and then you just multiply all the weights you have with the P, with the probability. Okay. And sort of one way of looking at this, you could ask, okay, why does this work? Okay, we said, okay, it works because we average over independent samples, and so we can reduce the variance. So that's similar to what we've done in bagging, right? That kind of idea. But here's sort of another aspect that I find quite interesting. So by dropping out units, the other units have to kind of make up for the learning that was previously done by certain, local region of units or one unit. So let's say you do some image classification or something, and one part of the network learned to distinguish me from a pig by looking at noses. Okay, so it just looks at the nose and it can distinguish my nose from the nose of a pig. Okay, but now this part is in one of these subnetworks. This part is away. So all the other parts now have to learn something different, right? So they might look at the tail or something, or other things. There might not be that much that distinguishes me from a pig. So I think it's sophisticated net, but it makes your network robust against learning, so that you learn different parts of find different aspects that need learning. So I find that quite a interesting sort of maybe too metaphorical, but nevertheless interesting view on this dropout network. So dropout, I think Joel also used dropout for the LSTM and said that it was without dropout, it didn't work at all. That's correct, Joel, isn't it? So there was just a dropout layer for the decoder that you did. But was that necessary or not? Did you check that? But it's a technique that's used, you know, very often for this neural nets, and so it's one of these standard things that now we know. Well, we have an idea of what they do and what they work. So thank you. Right, I choose the mask. So I choose the I here. So the mu I n. So it varies for I and it varies for n. So it varies at each step of the SGD, and it varies for each. Every single data point is a single mask. Every single step is a different mask. That's right. So the question was, for the ensemble methods in general, how many samples do we need to reduce the variance? That depends on this kind of, you know, how you construct. I mean, it depends on many things, but it depends on how you construct, you know, your models, if you make them independent or not. So if if they're more dependent, then you will need M much larger to get a significant reduction. Capital M much larger, yeah. But I guess it's like everything there, you know, people try it out, and so Joel's comment was that even if you know you don't choose your mask, you know, for different data sets, and you just randomly initialize your optimization scheme, you're going to end up in very different points. Like all your W's will be very different. So that already introduces some kind of independence, kind of. So that was this random initialization that I mentioned before, you know, that you can, that helps you to, you know, kill this term or control this term. Shows that each time we initialize, we start from a completely different place, and, you know, you don't end up at the global minimum, or I mean, there is no, you know, you're going to be at some kind of local minimum that we learned, or we hope is in value close to the global minimum, but it's very different in, you know, in parameter space. That's right. Yes. Did I understand the question correctly? That they should all, like, if I start with random W's and I let it run, that the solutions, the W solutions are all kind of close. Yeah, you're saying that the final W's are all close. That's the initial ones. Yeah, I think there are. Jody, didn't you mention that there is some kind of, you mentioned that in the first talk, there's a particular way of initializing stochastic gradient descent, right? So I haven't had the chance to look at that paper, but there are ways to do it smartly. But I don't know how it works. Is that Kahneman? The Bayesian brain hypothesis. Do you mean that we're actually bad at doing Bayesian computations, like the Kahneman idea of thinking fast and slow? Is that what you mean? Or, well, also decision making, I believe, is Bayesian, right? We have some kind of prior, like how you come up with your prediction would be Bayesian, I think, right? You would get you have some prior information or something. You know, I believe, you know, all the climate scientists they're lying, and, you know, you get some new information that, you know, that yet there's another kind of flooding or whatever. But you ignore that because you believe so much in, right? In that they're all liars, and vice versa, right? I mean, so like decision making, like, you know, to make it deterministic to come out, you know, to a decision is all. You can also see that as a Bayesian updating, right? You kind of weigh the uncertainty with the new piece of information that you're getting, and your prior, right? If you, depending on what you trust more, you know, your decision will be in one or the other direction. Question is, what's the application of having random outputs for each layer in a Bayesian setting? In what's an example where this could be helpful? Well, I can think of one in sort of in dynamical systems. So let's say you have a slow fast system, right? And let's take the climate, since we're there already. The climate or something, you want to forecast the climate, right? There is lots of weather kind of patterns give rise to the same climatic state. Okay, so you have like and so you could have probabilities associated with, you know, sort of one of those states that then would feed into the climate. So maybe that's, but I don't know how, are there networks that do this probabilistically? There's something called a Bayesian network, right? Or Bayesian networks. Is that Bayesian neural network? So that's the thing that you were. So the question was, if you're a working mathematician, why should you care about regularization? So Jordi is, I believe, referring to regularization is used a lot for overfitting. So if you have noisy data, then you might just, if you do some kind of regression, like polynomial regression, you fit the noise and you don't fit the signal. So if you get new testing data, you're doing a bad job. So that's why regularization is good. Whereas as a working pure mathematician, you will not deal with noisy data, right? You got your training set and everything is exact. But you still have that problem of variance reduction, right? You still have that problem of you need to explore your hypothesis space. So you decide on some kind of architecture, some network, and there is this huge space and you need to explore it. And you need to kind of find how, in what regions should you be looking for, right? And so that's where regularization helps, right? Again, like in this ensemble method, it just reduces the variance. You might have a model that gives you a lot of variance that has a low bias but high variance. So that's where it helps. It just helps in general with the generalization gap. Okay, and if you produce a generalization gap through overfitting and to noisy data, that's one situation. But you will always have a generalization gap because you don't have finite data, or you only have finite data. Sorry.